Okay, so hello everybody. Just a minute. So, okay. So today is first lecture last week before midterm exam, and plan is I want to finish section 3 today, okay? And next time, instead of starting section 4, which is already a somewhat different topic, we will make some kind of long, one lecture long summary of sections 1 and 3 before the midterm exam, okay? So section 4 will be started after the midterm exam by Marcus. Okay, so that is about that. And now let me return to what I was talking last time. So we were talking about sorting algorithms, and I skipped the first 3 because they are not they didn't require too much explanation. I have explained several times. And then we were talking about 2 recursive algorithms. The one was the MergeSort and the QuickSort. So now, just briefly, so what was the idea of the MergeSort? The idea of this MergeSort was to split the array into 2 halves, okay, size 1/2, and then to merge the 2 parts, to sort the 2 parts, and then to recombine. So this was the merging. Okay, so this was the merging part. And we discussed in detail what you can do. You always need some kind of copying. Okay, this was the problem of the merge sort. This merging part always needs a copying. So you can we saw that we can make the runtime O of n times log of n by using master theorem. And the memory consumption, the total memory consumption is on O of n log of n, but we said that we can reduce this by reusing memory. Okay, but you always have this copying problem. And the reason, one reason is that when you split the array X into this left and right half, so okay, you do not know whether everything on the left is less than everything on the right. This is why you need to do this merging thing. Okay, so so this was the problem, and now we said that there is a way to fix this problem by using a slightly different the idea of QuickSort. Okay, now so what was QuickSort doing? So the idea of the QuickSort is that you want to split the array before making the recursive call, so that everything on the left is less than everything on the right, and then you simply call this recursively, and then you are done. Okay, and this splitting was done here, and for later reference, I reference this as partition. So what did this do? We were choosing some element which we call pivot, and which is somewhere in the array, and then what this partition was doing is it moved the element somewhere here, and everything on the left is less than s, and everything on the right is bigger than s. Or let's say bigger or equal, but okay, this is a technical detail. I do not want to bother too much on this when you have what happens if you have several equal elements. Okay, so this is what this partitioning was doing. Okay, and once you achieve this, that everything on the left is less than everything on the right, you can simply call QuickSort recursively on the left and right part, and then you're done. Okay, so we can achieve that everything on the left is less than everything on the right with this partition. But the problem is that we cannot achieve that the parts are equal, or in fact, we cannot know how disbalanced this partition or left and right is. Okay, and that depends on the choice of this pivot element. And then we said you can choose this to some element in the array You can choose this to the middle element or to left element or right element, but whatever you choose it, you do not know in advance how well S separates left from right. Okay, S can be very small, very large, and this the one piece can be very big, the other one can be very small. And it doesn't help you. I mean, it doesn't help you to necessarily take the middle element, because the middle element is not middle big. Okay, after this process, it can turn out that it's actually the largest element. So you had this problem of this balance. Okay, and okay, this can now move left or right here, this A and B. So, and in the worst case, what you get is something like this: A and this division lands at the last element or the first element, and you have Tn minus 1 in the recursive estimate, which gives you O of n squared. Okay, and so in the worst case, this means that the QuickSort is as bad as the bubble sort. And it doesn't help you, for example, if you avoid the last element, it is the second last element that you get after this partitioning, then you have O of n plus Tn minus 2, and then you still get n squared. So as long as you have a constant here, you always get this quadratic estimate, which is not good. And this is why we try to improve this. Okay, we said you can choose this randomly. Okay, now that I see this, let me correct it. This of course should be the sign of an element. Okay, so you can choose a random index in this piece between left end and right end, and choose pivot randomly. But okay, this will be fine for maybe for average performance, but for worst case performance, you always have this problem. Okay, so this is what we discussed. So this means that in the worst case, QuickSort is as bad as the bubble. Okay, so this means if you have no control on the quality of pivot element chosen, you have this problem. And to fix this, we said, okay, let us assume that we can choose this pivot element so that this piece and this piece are at least epsilon times n. Okay, where epsilon is a fixed constant. So they are proportional to the size of the area. Okay, this is what is written here. So this means that then we can replace n minus 2 by n times epsilon and 2 by n times 1 minus epsilon. Okay, so for some constant epsilon which is between 0 and 1, and then I claimed that from here you can prove that you get the odd good complexity of O of n log of n. Okay, and the proof was per ansatz. So you simply write T of n of this form. You say I think that T of n should be of the form constant times n times log of n, and then you try to find the constant. Okay, and we found this constant by just by manipulation. So what we did is let me correct this here again. I said this why this happens last time, but this O of n, okay, which comes from this partitioning. Okay, so this is what cost me O of n. So this O of n, which comes from this partitioning, is some constant times n, which is a constant lambda. Okay, and then we said how we can calculate this C. And C was minus lambda divided over this star in parentheses, where this star in parentheses was this number. Epsilon times log of epsilon plus 1 minus epsilon times log minus 1 minus epsilon. And you observe two things. We observe that star is negative. So, okay, this means C is then, of course, positive. And we observe that when epsilon goes to 0, then the star also goes to 0, which means that the constant C goes to infinity. So this is epsilon here. Okay. I mean, drawing with a mouse is not the best. I should be maybe a little bit more careful. So this is an epsilon was 10. So when epsilon goes to 0, this expression also goes to 0 and c goes to infinity, which is the convergence to the worst case. Okay, in the worst case, there is no constant. There's no constant with c times n log of n is equal to n. You get this worst case limit here. So, but assume that as long as you can find some epsilon which is positive and satisfies this, then you can get this this good estimate of the of the QuickSort. Okay. So and now and then I discussed. So this was now the highlight of the last lecture. So I discussed an involved and tricky algorithm that can be used to produce you such an epsilon. This means I want to that produces me a pivot element. Okay, that I can find a pivot element S which satisfies epsilon is equal to 0.3 in let's say in the first case. So this is what we were discussing. And so how did this go? So now let's see. So the first thing that that we did is was okay, this is also framed here, but it is important. So let me move out some piece of this QuickSort algorithm into an extra function which I call partition. Okay, and so the goal of this partition was whenever I have, so this is XL and this is XR, and I choose an element, and now we have to be consistent. So please write here S, because in consistency with what I said before. So here is an element S. S is some element of this array between index L and R, so somewhere here. And what this does is it rearranges this piece of the array X between L and R. So here is now XL and here is XR. The element S is here, and everything here is less than S, and everything here is bigger than S. Okay, so we will need this. So this is what is called the partition, and we need this piece of code because we need to call this as an extra procedure later. So and how does this go? So we want to output an approximate median, so what we will output is we will output the median of 5 medians. Okay, so so one more time. You see, I can here. Okay, so this is the median of 5 medians. This is this element which is which we are going to output. And now what is this element? So first, for technical reasons, I said that there is no problem of assuming that all the elements are distinct. And so in order to avoid small technical problems, let's assume that all the elements are distinct. This is no restriction of generality. So I mean, learn what this means. If you do not know what this means, then please homework, understand the meaning of this abbreviation. So we assume that they are all distinct. And then what I do the following. I split my array into groups of 5, and why 5 and not 6 or 3 or 7, I will discuss later. So assume for now that we split it into groups of 5, and from these groups of 5, I determine the median, so the middle element of these groups of 5, which are these black dots, and I output the median of this median. And then we argued, let's say this must be here. Okay? So the median of 5 medians is at least 30% or 0.3 n away from the boundary. Okay, and the proof is simply per picture. So all the elements in this red area are bigger or equal to the median, and all these elements in this area here, okay, they are less than equal to the median. So, and for this, I mean, by a simple argument. So this is why the median satisfies 30, so an epsilon of 30%, or what I wrote, okay, I wrote this on the previous slide with epsilon is equal to 0.3 in the QuickSort. So we put this choice of pivot element into the QuickSort later. Okay, so okay, and now so this is what we were trying to output, and then I said, how do we do this? And we need two pieces for that. So we need a median of 5 median. So we need which is called later approximate median, and we need the order statistic. So we need two procedures. So to remind you what order statistic was, so the order statistic was that to output the index of an element in the array so that it has a given number k of smaller elements. And by assuming that all the elements are distinct, I said that this can be simplified now, that I can simply say k is equal to this number. Okay? And because the left side and the right side differ by 1. Okay? If they are equal elements, then sometimes m is ambiguous for given k, and for other k there is no m which satisfies k is equal to that. And to avoid this kind of problems, we have said we assume that all elements are distinct. So this means for every k between 1 and the size of the array, there is exactly one m which satisfies k is equal to that, and this is what is output by the k order statistic. So, and then we were discussing this in section 2, and we said there is a naive quadratic algorithm for the order statistic, which was very stupid. And then we discussed if the array is sorted, then it is very easy. Then you can simply output the k itself, which is all of 1. Okay? But of course we cannot use this here because we are trying to sort the array. Okay? But what you will see is, I mean, what comes out of this whole construction in particular is that you get a linear time algorithm for an unsorted array. So without sorting, you can still do this not in quadratic time, but in fact in linear time. Okay. This also comes out of this whole construction. So now how does this go? And we need two pieces. So the one piece is the order statistics, so which operates on a piece of the array x between L and R and for a given element k. And what the order statistics does is it calls the approximate median to determine a 0.3 approximate median, so 0.3n approximate median. Then you call this function partition, which I explained before, to split everything. So this, let's say this is S, and now this partition will split in everything into less than S and bigger than S. And now you know by your choice of element S that this is at least bigger or equal to 0.3, and this also is at least bigger or equal to 0.3n. This is important because then you need to call the order statistics recursively, okay, on one of these two pieces, depending on how the new position of this element S compares to K. I explained this last time, so this is what is written here. So now this is what the order statistics part is supposed to do. So the order statistics need the approximate median. Now, how does the approximate median go? Well, you do what we were promised to do. So we promised to output the median of 5 median. So you break the array into groups of 5. In every group you find the median. I said at this point, maybe remark. So how you find this median is, as long as you do not care about constants of complexity, it doesn't really matter. Okay? So because this effort, okay, here is for complexity reasons, this effort here is O of n. And the number of operations that you need to find the median in a group of 5 is only a constant that multiplies this n. So we have capital N over 5 such groups, and then this gets multiplied by a constant. Okay. Of course, the worse the constant, the more time you spend, but up to constants in n, it doesn't really matter. The important point is that you can always do this, for example, by sort. Okay. But later I will try to get a little bit more specific about constants. So remember that this constant in this O of n depends on how many operations you need to find the median in a group of 5. Okay. But as long as it's your constant, it's O of n. And then you call the order statistics to determine the median. So what order statistics can do in particular, I have n over 5 groups. Okay, so I have an array of these black dots. Ignore the other dots in the previous drawing. Look only at the black dots. Okay, I have n over 5 such black dots, and I can call the order statistics with half of it. So k is equal to n over 10. Okay, and then this will output me. Okay, this will output me this element, which is the median of 5 medians. So of course the order statistics is good enough to output me an exact median, because I can simply set k to be the half of the size of the array. Okay, so this is how it goes. And the interesting thing, the intricate thing about this construction is that both pieces, so both order statistics and approximate median, they need each other. Okay, so the order statistics need the approximate median in order to restrict the size of the area on which it calls itself recursively, and the approximate median needs the order statistics in order to calculate an exact median of the 5 groups. Okay, so every procedure needs the other. This is why this construction is so interesting, because you cannot do this with one. You cannot do this with one procedure. You need 2, and each one needs the other. So, okay, and now, so we were discussing the question why 5, and this depends on this complexity estimate. So when you have so how does this complexity estimate go? So let us do this first for the right side. So the approximate median has this O of n piece, which comes from here. Okay, so this was O of capital N, and now he's written O of small n, but it's the same. So, and then you have the order statistics applied on the array of the black dots, which is across 1/5 of the elements of the whole array, so 0.2 times n. And our estimate for TO doesn't depend on the k. So we say this is an estimate of the complexity regardless of what k, for every k. And now the right equation comes from the left. So what does the order statistics have of complexity? The order statistics calls the approximate median, so you have T of n. Then you have this partition. This is O of n. This comes here. Okay. And then you get this term TO of 0.7 times n, and I explained where this comes from. This comes from this piece, okay, which is a little bit vaguely written here, but I have explained very clearly what this does. So this is the maximal size of one of the 2 pieces into which the array is split after partition is called on the approximate median, and the approximate median is needed to bound this size. Since you know that the approximate median will be at least 30% from the left and from the right, the maximal size of one of these pieces is 70%, and this is where you get that from. Okay, so this is how you get this estimate. And now, what was the important thing? I said it, so the important piece about this estimate is that these 2 numbers, so 0.2 plus 0.7, okay, is equal to 0.9. So this the important part is that this is strictly less than 1. Okay, strictly less than 1. And then you can prove that this is linear. So now I said, okay, now you do not see this properly very well, but I prepared my own material which also goes back to this question: why should we take groups of 5? Okay, so why the median of 5 medians and not of 6 medians or whatever? So now let me go to my other material. So so you should be able to see this now. So this is now what I started showing you last time. Okay. So and then I discussed this question. So what happens if you replace the median of 5 medians by the median of k medians? Okay, so you can do this not only for groups of 5, but you do this for groups of k. And then I made the formulas, the equivalent formulas for what was in the yellow box at the bottom of the slide. Okay? So you get the approximate median calls this partitioning into groups of 5 and determining the median of these groups of 5, and then it calls the order statistics on n over k, because they're n over k medians of k groups. Okay? Where for later reference, I said that this O of n, to be more precise, consists of n over k groups times the complexity that you need to find the median of the groups of k. When we talk about constants later, this will be somewhat relevant, so keep in mind this phi k means the number of operations that I need to find the exact median of an area of k elements. So the concept will of course depend on what way I choose to do that. So I will probably, I don't see, maybe I will come to this at the end of the class, but for now it is okay just to remember that this is O of n. Okay, and then I explained this. So I explained this formula, and then I explained that formula, and this is when k is equal to 5. This is 0.7, and how does this come from? This comes from 1 minus the proportion of elements in this red area that you get, and this is k plus 1 over 4k. So as I explained, so this is when k is odd, and then I said for k is even, you have this problem that there are 2 middle elements. So when you have a group, okay, then there are 2 middle elements. And then you do not know which way to choose, and whatever you choose, you can choose the lower one always, you can choose the upper one always. One of these two pieces, okay, will be exactly k half, and this is why instead of k plus 1 over 2k, you get k over 2k, which is 1/2 times 1/2 is a quarter, and then you have here standing 3/4. The rest of the recursion remains the same. Okay, so and now what is the importance? So what do you get from that? And so now let's see, how can I do this? Yeah, I have to do like that. I cannot scroll without removing the annotate main. And now let me not make the mathematics at every detail, because it is not. I mean, it's not super complicated, and we don't have time for every detail. But so what you get at the end is for the asymptotic complexity is you get something divided by 1 minus the sum of this and that. So of this number, so 1 over k, and this number. And if you remember, if you put k is equal to 5, you get 0.2 and 0.7, and the sum of this is 0.9, is less than 1. And this is what I calculated here. Okay, this is what comes out in this sum. Okay, so now to return to the question why 5. Okay. In order this to be linear, what you need is that this sum is less than 1, and the sum is 3/4 plus 3/4k when k is odd, and 3/4 plus 1/k when k is even. You see that the sum becomes a little bit larger when k is even because of this middle element problem. Okay. So now you put k is equal to 3 and 4, and you see that what you get in this expression here, this expression is precisely equal to 1, and it doesn't work. So I mean, so what does this say? To make this clear, the algorithm will work. I mean, there is no the algorithm will terminate. You can do this for k is equal to 3, so for 3 groups and 4 groups as well. The algorithm will work, so it will terminate. But you do not have a provable linear worst case complexity of this algorithm. That is the problem. So the reason for k is equal to 5, okay, the reason why you need 5 is that 5 is the smallest k for which this becomes smaller than 1, and you have a provable worst case linear estimate, which is what you wanted. So you wanted to have a linear time algorithm. This is the reason why k is bigger equal to 5. So now, but now the question is do you need 5? How about 6? And the answer is yes, you can do that. I mean, you can simply put into the formulas and see that for every k bigger than 5, this is also less than 1, so you always get a linear time algorithm. Okay, so k is equal to 5 is the smallest, but it is not the only one for which it works, and it's also not the only one for which you get a linear time algorithm. It's just the smallest. And okay, the question is it the best? And okay, I do not want to get into this now. So what I will do is maybe I will, if I have time, I don't know, because time passes more quicker than I want, but if I have time at the end, I will discuss this issue with the constant. So, but let me, we have to better return to some main topic because I want to finish this, and in fact I want to use some of these things in what I would have to say about the constant. So our attitude so far was always that we ignore the constants, and so I will talk about this only as much time as I have at the end. So let me, we need to discuss two other important concepts that are at the end of the section, and okay, we try to get to finish this today. So to the summary of this story was that QuickSort is very bad, but we have found a way to fix it. Okay, so this algorithm now gives you a linear time estimate for epsilon is equal to 0.3, and by using the choice of pivot element which comes from this linear time median, you can get the QuickSort to be O(n) of log of n. Okay, so and now the next thing that is very interesting to discuss is that in fact is the proof that in fact n log of n is optimal for whatever comparison-based sorting algorithm. Okay, so this is very, I mean, okay, this is a very interesting point. So in fact, you can prove that QuickSort with the median, with the linear time median, or the merge sort, they are optimal. There is no asymptotically faster algorithm, and for this we need a little bit of theory. So so our goal is to prove that that n log of n is optimal, and we need something which is called a decision tree. So a decision tree looks something like this. So I have an array of elements which in this drawing, okay, in this drawing they are labeled as AI. Okay, and so what this decision tree does is it's a binary tree, and in every non-terminal node of the binary tree, there are two elements which indicate that the values of these two elements are compared. And there are two possible answers of this comparison. The one is the first element is less than or equal to the second, and the other one is the first element is bigger than the second. Okay, and depending on the result of this comparison, you go either to the left node to the right node, and then you continue comparing. Okay? So this is what is called a decision tree, and at the end, in the leaf of this tree stands a permutation. So this is supposed to be a permutation 312 in the meaning of, so what this is supposed to mean is that I take A3, A1, A2, okay, and I claim after making these comparisons here, and when I make these comparisons here and that I arrive at this node, okay, then the sorted version of the array is A3, A1, A2. Okay, this is what it says. So I have a finite number of comparisons, and at the end I have a permutation which tells me how do I have to permute the arrays so that the elements so that the array is sorted. This is what the decision tree is supposed to do. So this is what is written here. So and now you can simply test it. So let us do this. I think that there's probably an example. Let's say I take the array 2, 3, 1. Okay, so I compare A1 and A2, so 2 and 3. 2 is less than or equal to 3, so I have to go left. Then I have to compare 3 and 1. Now 3 is bigger than 1, so you have to go this way. Okay, and then I have to compare 1 and 3, so I have to compare this and that, and so I have to compare this with that, and simply 2 is bigger than 1, so I have to go right, and then I arrive here. And what this permutation now says is this is exactly the inverse permutation to this 2, 3, 1. And what this permutation says is that I have to take, so when I take 2, 3, 1, let's see, let me draw this. So x1, x2, x3. This is 2, 3, 1. This means, so what this permutation here says is that I have to take the array in this way, x3, x1, x2, and then it is sorted. And now let us test it. So x3 is equal to 1, x1 is equal to 2, and x2 is equal to 3, and the array 1, 2, 3 is sorted. So, and easy to see that this permutation here, which is in the in the orange in the orange circle, is exactly the inverse of that one. So, okay, so this is what a decision tree is. And okay, if the decision tree is correct, you can use this to sort a fixed number of elements. Okay, so this is what a decision tree is supposed to do. And now here comes so a lemma, which, I mean, I partly explained this, but I mean, think about it. So for fixed n, every comparison-based sorting algorithm, so this means an algorithm which uses this sort of comparison of worst case running time TFN can be unrolled into a decision tree for sorting an element of depth at most T of n. So when you have a running time T of n, then you have at most T of n comparisons, and you can then make out of this a tree where the path from the top to the bottom is at most T of n. So this is what is the depth of the tree. Okay. So you should think about it. How this is supposed to go. It requires a little bit of thinking. So basically, what you have to do is to create this tree. Is your algorithm. So whenever you have an algorithm consists essentially of two things. Either you test comparison or you swap. Okay, and so whenever you swap elements, every next comparison compares, of course, the swapped elements, but this corresponds to some comparison of the original elements, and this is what you continue writing in these nodes. Okay, and at the end, when you arrive at the sorted area, then you simply write the permutation that you got. So I mean, think about it. So this is basically an algorithm is equivalent to a decision tree whenever the number of elements is fixed. So every argument will give you a decision tree, and every permutation ends up in the unique leaf with label P inverse. This is what I explained here. So when I apply the algorithm on an array in which the permutation is written in terms of its images, so x1, x2, x3. So when x is a permutation, then this will end up in the leaf, which should be labeled with the inverse permutation. And the third one is, okay, now this requires a remark. A binary tree with n factorial leaves has depth at least log of n factorial. That is clear because the number of terminal nodes increases exponentially in the depth of the tree. So the number of terminal nodes of a tree of depth n is at most twice the number of terminal nodes of a tree of depth n minus 1. So the number of terminal nodes is exponential in the depth. This means that the depth is logarithmic, and since every permutation must be realized as a terminal node, you need at least depth log of n factorial. And now why this? So now here comes the big conundrum. Why is this true? Okay, so now probably most of you don't see why that is true. So why is n factorial log n factorial asymptotically equivalent to n times log of n? And that goes under the name Stirling formula. So for those who do not know this, so this is called Stirling formula. The Stirling formula, I mean, there are different versions of the Stirling formula, but let's see, can I write it somewhere where you can see what I'm writing? So let's see, let me write it here. So n factorial divided by n over e to the power n times square root of n is somewhere between, I think, e and square root of pi. There are much more exact versions of this formula, but this version should be more than enough for us. So from which you can see, and now this is something that you should be able to see, that log n factorial behaves like n times log of n. So this is now simple consequence of that. Okay, and this is what it was written in the previous slide here. And so this is where this comes. So I need this Stirling formula. You know, this is a place where computer scientists serve themselves on the mathematics. I mean, the Stirling formula has been around much longer before computers were around. but I mean, that's it. So this is how science goes. It's better. Everybody can benefit from everybody else. So mathematicians serve themselves on computers, but sometimes computer sciences need to serve themselves on the mathematics as well. So, okay. So for these insights, that what is the symptotic behavior of n factorial, you need the mathematics, and from this you get now this formula here. So this means you need a tree of depth at least n log of n. This means you need at least n log of n comparison, which shows you that algorithms with n log of n are optimal. And now the question is, how about other situations? You see, so this optimality depends fundamentally on the fact that I use comparisons to sort the array. Okay, so in my algorithm I compare elements, and this is the only thing that you basically have if you work with an abstract data type. So far, you see all the algorithms that we were discussing, we said we use an abstract data type, which we do not know much about, except that it has a comparison operator, and that's all we needed. Okay? And this is all we use. And in that case, this argument proves you that you cannot do with less than O of n log of n. Okay? So, but there are specific other data types which you can do better. Okay? And let me briefly discuss this. So one of these situations is when you want to sort according to an integer key. Basically, so what you have here is you can think of x in a sense that this is a record of data, and there is a component of it which is key and which is an integer, and I want to sort the records according to this integer. In the simpler case, you can simply sort the integers themselves, but it is sometimes more useful to sort the entire record. So, for example, I don't know, like you have people with birthdays, and you want to sort them according to their age. So you do not want the birthdays, only the birthdays, but you want the entire record of the person, but sorted according to the birthday. So, and we assume now, this is important, that the value set is an integer, the integers from 1 to n. And then we do something like what we did in this database uniqueness algorithm. So what this CountingSort does is it simply records for every key how many times the key occurs. This is what is done here. So if I have a number capital M of keys, I write into an array indexed by the key how many times the key occurs, how many elements in X have this key. Okay, so this is what I write. And now, and then once I have this, so for example, in this example, I have keys from 1 to m, and then key 1 occurs 3 times, key 2 occurs twice, key 3 occurs 4 times, 5 and 6, 4 and 5 do not occur, 6 occurs once, and 7 occurs 5 times. Okay, and then what you write in this record is you have to write the 3 elements with key 1, the 2 elements with key 2, the 4 elements with key 3, then 4 and 5 there is nothing, 1 element with key 6, and 5 elements with key 7, one after the other. And this is essentially what this code does. So here in this piece, you count the elements for a given key, and once you know how many elements there are for a given key, you can here adjust the index of the sorted array in which you write every element in X. So when you do the way that this is done here, count of m before this final loop goes is the maximal index in the sorted array into which you write an element from x whose key is equal to m. Okay, this is what this does. And when you do it in this way, you see that this count is continuously decreased. So it will write the elements when I go in x equal elements with the same key from left to right will be written in the array y from right to left, because I take the maximum and then I decrease. But okay, this is only a technical detail. So the important thing is that everything which is on the right gets a value of the key which is not smaller. This is the specification of QuickSort. So if you have several people with the same birthday, it is not specifying in what order you write them into the array. You know only that older people should be before them and younger people should be after them. But in which way you write the people with the same birthday, it doesn't, it's not specified. So in this case, if they will be written in the opposite order in which they occur in the array X, but it is not important. So this is what you can do, and this essentially exploits the fact. Okay, this fundamentally exploits the fact that the keys are integers, and you use this value 1 to m in order to index elements in an array. Okay, so. And what is the runtime of this? Okay, so you have loops from 1 to m and 1 to m, so the runtime is n plus m. So this is linear in n, but you always have this piece with the m, and I explained this at the time of the database uniqueness algorithm. Okay, that you need this, so you need the memory consumption for m, because you need to create this database here. So you need to specify this array count, which will cost you m. Okay, but you also need this m in the running time, because, for example, you need to initialize, and later you also do that. Yeah. So this will contribute something with m. And okay, so this is what you get. So again, I said it at the time of the database algorithm, but obviously there is a problem when m is large. You see, so when m has extremely many values, then this will become a problem. So this will become both a runtime and a memory problem. And it's something that you have to consider. So for the price of your running time being linear in n, okay, you pay this price that when m is large, you have an extra large running time and memory consumption. So, but it's something that you cannot avoid. And obviously, this is now slashed here because this is not a comparison-based algorithm. So I simply use that keys are integers and I can order them in an array automatically. I do not compare the keys. So this means if you have specific data types where comparison is not needed, you can do better. So you can do, for integer, you can do this CountingSort, and then there is this RadixSort, which is kind of similar. So this is an algorithm which is there for sorting sequences of binary sequences, or sequences of 0 and 1 in lexicographical order. So this means 0 and everything after it is always smaller than 1 and everything and whatever after. Okay. And the idea for this RadixSort is, so this is a bit sequence of fixed order. So this number m is the same for every element of the array small x, and it is fixed. So it is not, it has to be fixed in advance. Okay, and how do you do this? Well, this is essentially a version of the I mean, it is a version of the QuickSort, if you want so. So in the QuickSort, we had the pivot element, okay, and then we sorted everything on the left less than equal to everything on the right in this procedure partition. And now to emphasize the analogy, so sometimes this was written split and sometimes this was written partition. And we have to, I mean, probably we have to fix the slide the next time. We have to stick with one name. So the meaning of this this split is the same as this of the partition, except now that the meaning of this M in the partition is different. So what we did for the QuickSort is we used the reference element. Okay, so there was a pivot element, but in this case, we simply look at bit number M. So we look at the M element in this sequence. Okay, and this bit has only two values, 0 and 1, and then you do not need the reference element because basically you can simply say everything which is 0 should go on the left of everything which is 1, and this is what you're doing here. So this is not written in pseudocode, but it should not be difficult to make the pseudocode for this partition. So the partition simply puts everything which is which has 0 on the left of everything which has 1. Okay, and so this proceeds. Say, let's say with I mean, in this case, the bits are ordered in the highest value, the highest valence bit is ordered first. So this is, but this is called mth bit. So you start with the m bit and then m minus first and etc. Okay, and then so what you do is you split it according to the mth bit, so that everything with mth bit 0 is left of this middle mid element, and everything which is 1 is it's right of this mid element. And then you have everything with 0 on the left, everything with 1 on the right, and then you continue splitting this according to the m minus first bit. Okay, and then this simply calls itself recursively. So every piece in which there is 0 is now split according to the second bit, which is m minus 1, and then recursively this will sort you the array. Okay, so now there is a little bit of so again, this is not a comparison-based algorithm in the sense that so I compare only zeros and ones. So and what is the number of operations? Well, I mean, it is now a little bit different from the QuickSort, because the recursive calls of this this procedure change the position of the bit which is considered. Okay, and now you can very easily see that every element in the array is examined and swapped all of 1 times according to each one of its bits. And so since there are capital N elements with small m bits, then there are capital N times m operations of this, or constant times that. So you get something which is linear in the elements of the array. And if you look into the bit cost, okay, now you have capital N times m operations on sequences which have m bits, so you have to multiply this one more time by m, and you get a capital N times n squared. So this is the bit cost if we regard every 0 and 1 as a bit of this data type, which is a little bit abstract, but okay. You see, in general, we did not talk about bit cost about comparison by sorting, simply because we're working with abstract data types where we cannot say how this is implemented, and so bit cost doesn't make much sense for an abstract data type. I said this from the very beginning, but in this case, when you assume that every element in the sequence is a bit, then you can estimate this bit cost. And now you can compare this to the MergeSort, and you see that the bit cost is n times log of n times the number of bits of this, which is this number. And so what you can see from here, for example, is that when this RadixSort algorithm is efficient when n is very large. Okay, when n is small as compared to m, then the quick and the MergeSort may be more efficient. So, and last thing to discuss probably, so in order to finish the for today is the parallel sorting. So we didn't talk about parallel computing very many times, but there are ways to speed up sorting procedures when you allow parallel operations. And for this, we use this model with primitive gates. So you assume, let's say that you have a set of elements with a total order, and you have a fixed number, capital N of elements as a size of array. Okay, so the size of array is 6. For example, in this example here, okay, so in this example here, I'm taking n is equal to 4. So I want to sort 4 elements of the data type X, where I'm using comparison. And what I draw is this vertical line, which is called a primitive gate, is a piece of operations which simply compares xn to xm, and if the left one is bigger, then it swaps them, so that the left one is always smaller than the right one. Okay, so this is what this is supposed to do. And now I can, whenever I have a sequence of such primitive gates, okay, I can simply process them. So now this is what is done in this example. So let's say I have 3, 2, 4, 1. Okay, now I pass through this gate here, which says I compare 3 with 4, and if 3 is bigger than 4, I solve, but 3 is less than 4, so nothing changes. Then I pass through this gate. Now 2 and 1 are compared, but 2 is bigger than 1, so I have to swap them. Now 1 is here and 2 is there. Then I have to pass through these 2 gates, 3 and 2 and 4 and 1. Now in both cases the upper one is bigger, so I have to swap both. And finally I have to pass through a gate where you have now element 2 and element 4, element 2 and element 3, so this is here. And 3 is bigger than 2, so I have to swap them again. And now when you do this, then you see that 3, 2, 4, 1 land at 1, 2, 3, 4, which is sorted. And now, okay, now this works for this permutation, but in fact, you have to do this to check that this is correct. You have to do this for all the permutations, so all 24 permutations. Okay, I mean, as an exercise, try it out. Okay? And you will see that if this is correct, then at F for all the 24 permutations, you will always land at 1, 2, 3, 4 at the right. So this means that this here, you can understand it as a sorting network. This is what is called a sorting network. So it is a network of parallel gates, each one primitive gates, each one which has this functionality, and the result is that in what order you put distinct elements on the left, they all come ordered on the right. So and now okay, we can test that this is now a sorting network of 4 elements. And now why am I discussing this? Okay, because the reason is that you can use this to speed up. So now you see there are 5 comparisons which are made here. Okay, but whenever you have comparisons on this joint pair of elements, they can be done simultaneously. So there is no problem, okay, do these 2 things simultaneously. So for example, I can do these 2 things simultaneously, and this is the reason why they're also drawn like that. So they are drawn one below the other to indicate that in fact you can do this comparison simultaneously because they operate on disjoint pairs of elements. And similarly, although you cannot draw this one below the other, these two can also be done simultaneously. And so they do not compare neighbored elements, but still the two pairs are disjoint. So I can compare 1 with 3 and 2 with 4 independently at the same time, and swap them if necessary. But I can do this simultaneously. So this means that if you parallelize this, you can actually achieve these 5 comparison swap primitive gates. You can do this in 3 steps. So the parallel complexity of this is 3, not 5. Okay? And now you can use this idea to try to parallelize some sorting networks that we have in some form learned. So what is this now? Now this is you see that this is a network for 6 elements. Okay? And in fact, if you do not see this, I mean, okay, we do not have. I mean, I have been already pretty much have gone into detail on pretty many things. So if you do not see this, exercise yourself. What I claim is that this sorting network is in fact the one that comes from the bubble sort. Yeah, because what does bubble sort do? You compare neighbored elements and move the upper one to the right. So and this is exactly what is done here. So I compare 1 with 2, 2 with 3, 3 with 4, 4 with 5, 5 with 6, and then recursively you decrease the right boundary. So at this point, the last element will be the maximum, and then you sort from the right. Okay, and in fact, what you see that in fact this network is the network, the sorting network of the bubble sort. Okay, and now we saw that the complexity of the bubble sort is quadratic. Okay, now the number of comparison is quadratic, so the size in terms of the number of gates is O of n, O of n squared. But if you parallelize this, then you will see that actually you can do this into into O of n, namely. So what you can parallelize, let's see, when I can draw this. So this one will go for itself. This one will go for itself. Then you do these two parallelly. Then you do these two parallelly. Okay. Then you can do these 3 parallelly. Then you can do these 2 parallelly, these 2, and then this and that. So and okay, now it's not a very good drawing, but so think about it. Whenever you have a pair of disjoint pairs of elements to compare, you can always put them at the same height, and then exercise see that this O of n squared elements can be put into O of n positions, so from left to right, which means that as a parallel algorithm, you can achieve bubble sort to run in O of n. Okay, so now I mean this is of course I mean it is an idealized situation, because what this says is essentially that you are allowed to use at the same time an unlimited number of CPUs, which is not the reality. Okay, so it is not clear that you can do at the same time an unbounded number of operations. But for theoretical purposes, you can certainly say you can parallelize the bubble sort to become linear time. So and now to the outlook of this section and this whole topic. So this is a theorem of theoretical computer science, which more or less explains the importance of, if you want, so the importance of parallel sorting. So the first part of the theorem, I don't want to, I mean, the proof of this is not in the scope of this class. So the theorem which says that if you have a sorting network which sorts all sequences with values in 0, 1, then you will have also a network which sorts correctly sequences in any data type. So you can restrict yourself to sequences of 0, 1. Okay. And so this means you can simplify the problem of finding correct sorting networks when you restrict yourself to sequences to array elements which are 0 and 1. So okay, and the other piece of this this theorem, which is more interesting, is that there exist sorting networks of size O(n) of log of n. Well, this is, I mean, this is more or less nothing new, because I think this is what we essentially discussed. Because whenever you have a comparison based sorting algorithm of complexity n of log of n, you can make this into a sorting network with n times log of n gates. So this is not difficult. I mean, this follows more or less from our discussion of the optimality of MergeSort and QuickSort. So this part is known to be, and this part is also known to be optimal. So you cannot have less than n times log of n gates. But the interesting part, and unfortunately this is now beyond the scope of our lecture to prove this part, is that actually you can arrange this n times log of n gates parallelly into depth O of log of n. Okay, so this means, if you see here, our bubble sort, we were able to make it linear, but in fact what this theorem tells you, that actually there is a logarithmic time algorithm. So if you allow parallel sorting through networks, then there exists actually logarithmic time algorithms for parallel sorting, and the assumption that, of course, you allow to use an unlimited number of parallel comparisons at the same time. Okay, this is of course ideal, but anyway, for the purpose of theoretical computer science, this is a very, I mean, interesting result. And I mean, this is what it's an outlook into what complexity theory looks like. Okay, if you want so. And now I think I have now 2 minutes. So I think I stopped sharing. I thought that I think it is not the best idea to go back into my discussion of constants in the median of k medians discussion. Okay, so let me not go back to this. We have only 2 minutes, and it is not worth now trying to do this technical part. And it's not so particularly important. So okay, I will share this material with you. I mean, I typed it, so it is for you. I will share this material with you. You can read what I have written there. And the upshot of this story was that, in fact, it seems very likely that 5 is not the best. So I said that this will depend somewhat on what algorithm you choose to find the median of the K group, but particularly the faster algorithm you choose, the more likely it is that larger groups will do better. Let me say it this way. So particularly if, for example, you use QuickSort and then to sort the K group, and you find the median of that K group, then probably using groups of size 9 or 11 looks to be the best. Okay, but maybe let me leave it as a challenge to you. I mean, if you understand properly what I have said, you will have no problem in writing a computer program which does it, and then you can simply test it. And that would be very interesting to see, to learn what results you get. You can measure the CPU performance, for example, of the program. Okay? So take some array which is sufficiently large, say, I don't know, 100,000 or somewhere between 100,000 and a million integers, okay, and implement this algorithm with everything, with k, everything from 3 to 15, okay, and tell me what running time you get. I have some prediction, but let me not get into this. So the ultimate proof for yourself that you understood how this median of k median works is to have a working program, and then you can experiment with it. So my guess is probably that k is equal to 9 or 11 will be the fastest in terms of constant, but I cannot be, I'm not sure, but anyway. So this is as far as I wanted to say about I mean, as much as I had time to say about section 3. So I didn't do a summary of it. Next time, so I will do then the complete recap of sections 1 to 3, including my own summary of section 1, which was taught to you by Martin, but okay, you will have my own version of my own short version of section 1. Okay, so this is for today. Okay, see you then on Thursday, last lecture before midterm exam, and then I will do my summary lecture. Okay, thank you.